Okay, welcome back to soil mechanics module. And then thank you for being here in the early in the morning. So today I will be discuss about unsaturated soil mechanics. As the name implies, it is soil mechanics, but we have adjective unsaturated. It means that our topics we dealt with in these modules are all saturated soil mechanics. Your groundwater level is at the ground surface. Below the ground surface, all soil are fully saturated. All voids filled with water. But in natures, you can just turn around and then see that out there, your slopes, your roads, your plants, all are unsaturated. This is a natural process. Unsaturated soil means we have certain void ratio. In that void, partially filled with water and air. The biggest different thing is air. Air involved in our soil mechanics. This air play a crucial role in our engineering behavior in terms of hydraulic behavior and mechanical behavior. This is a Loyang Avenue slope failure video. Wow, soil looks like fluid, right? Wow, flow down. Such a huge, more than 30 meters. How about this? Slope failed and turned into debris flow. This is the occurred in 2021. This one also 2021. More recently, 2025, Bukit Hillside Park. It looks very shallow, but somewhat dangerous under the Bukit granite residual soils. Naturally formed slope. How about this? Telok Blangah. Such a huge scrap underneath Jurong formations. This is a Jurong formations, Bukit granite, and the Kalang formation. Hi, Pro, why you showed me slopes? Slope failures. Mostly every slope is the unsaturated soils. And then during the rainfall, slope getting wetter and wetter and ended up fully saturated conditions. In the meantime, soils shear strengths gradually decrease and slow failure occur. Such failures unavoidable. Seoul, 2012. Another camera view. Singapore is no exemptions. This catastrophic slow failure can result in expansive disasters, and their impact is not limited to remote or rural areas, causing significant risk to urban infrastructure. Why these slow failure happen? In most cases, they're closely linked to rainfall, water infiltrations. We discussed, we learned, right? Water flow from here to here due to total head differences based on barren equation. Then, microscopically, water flow through what soils in accordance with Darcy's law. From the Darcy's law, we can pick up Q, flow rate, KIA. K is the source permeability. I, hydraulic gradients. A, just area. Okay? This rainfall flow through slopes due to total head differences. And then while run off and then seep through into the soil. Now Darcy's law governs the water flow. Let's consider this typical slope. Actually, it is unsaturated soil slopes. When it rains, water infiltrates into the slope and become progressively wetter. So water contents increase. Why, Prof? Something weird terminologies. SWCC. Only I know soil permeability, but unsaturated permeability. Totally new terms. Later on, I will explain how this parameter affects our water content variations. It is not a static. It fluctuated and varied with something. Okay, simply when it rains, soil's water content increase. Good, moisture content increase. This infiltration changes my hydraulic conditions. Specifically, matrix suctions. In unsaturated soils, there will be air, right? This air forms certain pressures. say suction pressures, say negatively developed, negatively poor water pressure is developed. Poor pressure always positive, hydrostatic, right? But in the unsaturated soil, suction pressures same as the negative water pressures. These suction pressures pull soil particles. Can you imagine? You can prepare some plastic bag and put some soil samples, and then you can squeeze, and your soil particles packed. These suction pressures take place in the void. So soil particle closer, and then strongly bonded with suction pressures, negative water pressures. That's why in unsaturated soil conditions, their strengths, so-called shear strengths, our next topic, increase. But water infiltrates, and then this water gradually filled in your void. This air pop out, no more suction pressures, because these suction pressures mostly came from air. Water comes in, air goes out. So metric suction decrease, and my shear strength decrease. Very bad situations. Very negative impact. And then ultimately trigger slow failure here and there, and then they flow down, they will flow, and then decompose it. For example, your HDB here, your debris flow hit your HDB, hit your condominium. Quite dangerous situations. High prof, we can protect, of course. We can use, we have several approaches. Here's only two things. One is the finite element analysis. The other one is the limit equilibrium analysis. Both are the software-based analysis. From these analysis and design, we can protect, reinforce such slopes likely to fail. But this watershed, this small, for example, this area is a from out there. I can simulate from out there using these. But these slope failures often occur on a large scale. They are very widespread and affect multiple areas simultaneously. As a result, traditional methods are limited in their ability to provide effective and timely response to slope failures. So I propose regional scale analysis approaches. This means that we incorporate spatial data into our assessments, including soil properties and digital elevation models, DEM, groundwater table distributions, and the rainfall and bedrock and all the topographical informations. These are all GIS-based data sets, which can be visualized in the certain software, ArcGIS, ARCGIS, ArcGIS. So once the data layering is completed, we define our analysis domain, entire Singapore. But we need to divide it into small zones for the effectively analyze. So I've conducted regional scale analysis to obtain such factor of safety map. Here is the slope, right? After the rainfall, this slope tend to move. This is a driving force. But our soil has our own shear strength, right? Resist force. The ratio of driving force to resisting force. This is the factor of safety. So I've analyzed rainwater infiltration analysis with the incorporation of unsaturated soil characteristics. Then I put up on slope stability analysis to calculate driving force and resistant force with the incorporation of unsaturated characteristics. I ended up with our factor of safety map. Lead, very dangerous area. This is the Orchard area. A lot of dangerous areas. This analysis was done by very heavy rainfall, considering climate change. How many times have you heard about unsaturated soil characteristics? A lot. It means that unsaturated soil is the key in analyzing slope stability to manage debris flow, landslide, or about unsaturated soil mechanics. $700, $800 pages book for unsaturated soil mechanics. But in short, only 50 slides. I do believe today's lectures gives you a little bit clear aspects and then clear big pictures in your future careers. Because this is a totally new concept. I've been studying unsaturated soil for 15 years. Back then, everyone said to me, why are you studying unsaturated soils? Because all design is the conservative, but unsaturated soil is quite a reasonable and an economical design. Why? Unsaturated soil. Poor air pressure exists. It means create suction pressures. It means your strength increase. It means your design is quite economical. You are not supposed to go this way. But BCA adapted unsaturated soil analysis. In Korea, all slope design have to be analyzed based on unsaturated soil mechanics. So I briefly introduce the unsaturated soil mechanics, and then I will explain the unsaturated soils mechanics in terms of theoretical approaches, and then laboratory, and then applications. So unlike saturated soils, one pretty big advantages of being unsaturated condition is to have additional shear strength that comes from existence of matrix suction in soil. Pop questions. Is it true or not? In recent years, some of the greatest cost benefit associated with geotechnical engineering is related to the application of unsaturated soil mechanics to the near ground surface. Is it true? I would say true. Another question. Is it true or not? Application of unsaturated soil mechanics to the near ground surface require a vision and innovations on the part of the geotechnical engineering community as well as the regulatory agencies. Also true. Innovative, economical design, optimum design approaches. That's why last year, BCA announced new slope design guideline by using unsaturated soil mechanics to take into account climate change. Due to the climate change, severe weather events, rainfall intensity, rainfall period, quite getting severe. Our slope quite vulnerable, prone to failure. So, Our geotech engineer, even our soil civil engineers, geotechnical engineers, need to accept responsibility to show governments, authority, and company clients innovative engineer solutions. Unsaturated soil is innovative engineer solutions. Result in financial benefit, reduction in risk, provide greater flexibility, climate change. Let's think of geotechnical structures, slopes, retaining wall, tunnel, foundation system, piling, MRT station, underground structures, all are our geotechnical structures, and the adjacent soils all are unsaturated conditions. Okay, let's define unsaturated soil zone. Unsaturated zone. USGS, United States Geological Survey, we so-called USGS, define that part of the earth between ground surface and water table. Okay, part of the earth. This term mostly comes from engineering geology, and just focus on ground surface and water table. Water table here fully saturated, but ground surface, water table here, oh yes, in between ground surface, water table. This is the unsaturated zone. Also, some other institution define negative water pressure. Oh yes, ground surface, water tables. This area, there should be some air and water in the void, right? Air create suction pressures, negative water pressures. Oh yes, the soil in between these two, there will be some negative water pressures. Below the water table, hydrostatic pressures. In between ground surface and water table, there should be unsaturated zone, which has negative water pressures. At the beginning, here's the water. Degree of saturations, 100%. Makes sense. Gradually decrease, 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 decrease near ground surface. Mostly dry. I feel dry. Very lower level of degree of saturation, right? Such characteristics, 100% degree of saturation near the water table. Yes, it is true. And gradually decrease. But due to the soils in between these ground surface and water tables, their permeability, their pore shape, based on these hydraulic properties, this shape should be different, right? Something significantly drop and constant and still 100% and suddenly decrease, something like that. This characteristic can be measured. And then the final product of the tests is soil water characteristic curve. Soil water characteristic curve, SWCC. Just above the water table, we have capillary zone. So water goes up a bit. We still consider as a saturated zone. And then now we can see air pressure here and also dry zone. Below the water table, the pressure is a hydrostatic pressure, right? And then above the water tables, negative water pressure. This is the unsaturated zone. Three different protocols. First one is the theoretical equations, theoretical approach. Theoretically, we develop certain formula to solve mathematically. Second one is we measure something. Soil water characteristic curve. Unsaturated permeability. Mostly get it from laboratory tests. Unsaturated soil permeability. Our soil's permeability tend to the power of negative 8, 7, something like that. It is constant, all the way constant, but unsaturated permeability varies with respect to the metric suctions. When you have a metric suctions, your permeability increases, decreases as compared to saturated permeability. Definitely drop significantly. Water cannot flow easily because your suction pressures pulls your all the soil particle each others, and then your channel is quite narrow. Initially, water try to infiltrate. Oh, very difficult. Keep try, and slowly goes in, and then these water infiltrations reduce metric suctions, and their channel smoothly release, and then up to released up to saturated condition. And then also numerically we solve the typical issues, kind of slope failures. Using Plexis, Midas, any other geotechnical and commercial software, we also solve. Unsaturated soil mostly consists of water, yes. Soil particle, yes. Air, yes. Just now, I explained to you. Our unsaturated soil adapt air pressures. And then contractor skins, kind of membrane, elastic membrane, air-water interface, acting like an elastic membrane by pulling the soil particle together. These create suction pressures. Total stress minus pore water pressure is effective stress. Can you remember? This is for saturated soils. But unsaturated soils, we have pore air. Total stress minus out pore air pressures. Pore air pressure minus pore water pressures. The first term is the net normal stress. Second term is the metric suctions. UA minus UW. Air pressure minus pore water pressure. High probe. I can't feel any air pressure, right? Which is the atmospheric pressures. Consider as 0. 0 goes to here, 0 minus UW. 1. Pore pressure, negative. Yes. Metric suction is UA minus UW or negative pore pressure. Why we need UA here? In our laboratory, we can't form unsaturated condition in our lab as our nature conditions. So we apply air pressure into the soil. So metric suction 10 kilopascal mean we pressure certain air pressure. Metric suction 20 kilopascal, we increase air pressure to form 20 metric suction. That's why we still need UA terms in our theoretical equations. These terms, sigma minus UW, sigma minus UA or UA minus UW can be shown in our shear strength. Okay, shear strength is the next week terms. Oh, next week is a recess week, week 8. Just wanted to highlight that on such soils, we still also have net normal stress here and metric suctions. C prime plus. Oh, it means that this term is the additional shear strength, right? Oh my goodness. UA minus UW metric suction term also plus additional shear strength. It goes to 0. It goes to 0. Same. UA0, UA0, and then this term goes to 0. Became same equation of saturated conditions. Hyper, something weird terms here. I know, phi prime. This is the internal friction angle, right? What is the pi b? Wow. When you have metric suctions in your soils, and then you're gonna do triaxial tests, no worry, this is also conducted in our after recess week. You will see this. From your shear strength tests, triaxial tests, mostly we only draw this curve. X-axis, Y-axis. Only we consider these two-dimensional Moore circles. But we have another axis, matrix sections. And then we plot again. And then we have certain inclination. This is the x-axis, y-axis, z-axis. But this is not the plane of it inclinations. This angle is the pi b. This pi b angle only exists when you have matrix suction, because this axis is a matrix suction terms. I'm quite confused. I don't understand what is the net normal stress, shear stress. No worries. Later on, you will see, and then you will learn about this. The important thing is, after the triaxial test, we are supposed to plot this Moore circle, X and Y, and plot only these things, but we have another axis, matrix suction terms, and plot, but this term a bit shifted up. These pi b angles create additional shear strengths. Okay. For the unsaturated mechanics, I emphasize that we have three things. First one, soil water characteristic curve. Degree of saturation, fully saturated, gradually decrease. Such relations, such shape can be obtained from lab. Temperature cell, pressure plate cell. We have certain 5 or 6 methodologies to get. And then unsaturated permeability, right? Due to suctions, the soils packed closely. Their void quite small. The suction pressures create smaller permeability, and water keep trying to infiltrate, and water slowly goes in. Initially quite slow because low permeability, and then keep trying and getting higher and higher up to saturated. Such relationship can be obtained from laboratory or statistical method. And the last one, unsaturated shear strength, pi b. During the tests, we control pour air. That's why we definitely know pour air minus pour water pressure, right? Which is the metric suction. We know we control metric suctions. That's why this is already the given conditions. So from the triaxial test, what we're gonna get is pi b. Z-axis metric suction and inclination, this angle. So first, soil water characteristic of, which is the relationship between water content and metric suctions. Wow, okay. And Friedland mentioned that relationship between degree of saturation and matrix suctions. Okay. Can you convert your water content to degree of saturations? Yes. What is the important thing is water contents, degree of saturation, quite similar meaning, right? These quantities varies with matrix suction. Like this. Hi Pro, what is the gravimetry water contents? No, I usually use volumetry water content. Water content, gravimetry water content, volumetry water content, degree of saturation, all are similar quantities. You can freely move and express different way. But this quantity tells you how much water I have right now, right? This water, mostly fully saturated conditions, 30%. In, in total, your mass of water is 30% compared to total weight. Volumetric water contents expressed in terms of volume. 30%, still 30%, still 30%, still close to 30%. And at a certain inflection point, drop. Wow, drop. It means pour air goes in, water goes out. And residual states. You see, here metric suction around only 10 kilopascal. But in your unsaturated zone, two-phase zone, your metric suction is around 100 to 1000. Wow. Your suction pressure is quite high. How do you get this such curve? Soil water characteristic curve. Okay, this is to see this. You prepare saturated soil first, and then we apply air pressures. This space packed with certain air pressure, right? These air pressures force water to drain out. Water goes down and then drain out. And these soils gradually dry and dry because water flow in, water comes out. Can you imagine these situations? Then we can measure the height of the water, amount of water from what soil samples. We know applied air pressure, right? We know the water comes out from the soil, right? We can figure out water volume changes. And then with the different metric suctions with time. Every point goes here, each point. And then now we can have smooth curve, soil water characteristic curve. Hi, prof. This is just curve. no digit value. How do we apply this curve to our tulip design? Yes, good questions. We have certain parameters we can pick up from this curve. First one is air entry value. Air can enter your void. Just start to enter. Then you can see the pressures. Roughly 8 kilopascal, right? These pressures. After beyond these points, your soil start to be unsaturated. 0 to 8 kilopascal, I keep blow air up to 8 kilopascal, but water still in the soils. The air cannot go in the soils. But 8 kilopascal, 9 kilopascal, water just started go in. The soil start to be unsaturated conditions. This point is air entry value. And then the prevalence proposed fitting parameters A and M. Certain A is the quite close to air entry value. N is the slopes of the decreases ratio. M is the control, something like uh, the shape, the entire shape of this curve. So in your numerical analysis, what you can do is just key in A and M. Then the system automatically generates such curve. Can you remember we blow in air pressure and water comes out? This soil perspective, soils underwent drying, right? This is drying curve. And then vice versa. Water can go in, water comes out. Wetting cycles. So drying and wetting, drying and wetting. We have different. But in terms of our laboratory perspective, drying curve is much easier than wetting. Drying, we're forced to apply air. It's gonna take 1 week. Wetting, we can't apply the pour water pressure directly because the soils can be disturbed. So it's gonna take 1 month, 2 months. That's why we normally use the drying curve. Next, permeability. Unlike saturated coefficient of permeability, which is a constant, the unsaturated one is the not constant. This is important. And then mostly, when you key in your soil water characteristic curve, entire shape or A and M, you can automatically draw permeability functions. Why? Of course, theoretically, we create our permeability from the mathematical formula, and also we can obtain our unsaturated permeability from the laboratory tests, even these statistical models, but quite complex. Let's think about these relationships. Your soil water characteristic curve. I just mentioned to you, once you key in this soil water characteristic curve, you will have permeability functions. Why? They are quite related to each others. This point is air entry value, right? Just start to be unsaturated condition. Air pressure, my air can go in at this point. It means that before this point, soil still saturated, still protect myself. Oh, please do not come. I hate my air. I hate air pressures. But as of certain pressures, okay, come in. Start to drain out water progressively and getting unsaturated conditions. Unsaturated condition meaning suction pressure due to air, right? It means that your permeability significantly, drastically drop. You see? Okay, the red one, 10 to the power of -6. After air entry value goes down, wow, 10 to the power of -7, 8, 9. Wow, water cannot go in. It is most like clay. It is most like sand. Because the saturated permeability is something like 0.1. The unit is a meter per sec. This is the laboratory test and the fitting parameters. This is also laboratory test. The dot is the laboratory test, and then line is the fitting line. So we just clear two items. Soil water characteristic curve and then unsaturated permeability. What is the last one? Shear strength. Pi B. Pi B. X, Y, Z angle. Just heads up the actual tests. In week 8 and 9, I will explain these actual tests. But different thing is, you see, okay, let me see this. Number 3, poor air pressure. Normal saturated traction tests, we don't have poor air pressure line. But in the unsaturated soil tests, we have poor air pressure line. I apply poor air pressure on top of the soil sample and then form a metric suction. This is a real situations. This is the undisturbed soil sample from our project site. And these are theoretical drawings, more circle, and then we have another axis, and then we have draw another more circle, and then we will get the pi b angles. This is the typical results of the triaxial tests. We apply load and reload. Increase your metric suction by applying poor air pressures, and then load, reload. Also increase one more time, load, reload. We use the multi-stage unsaturated tests, and then your shear strengths can be plotted with respect to metric suctions. At the beginning of your metric suction from 0 to 80, here's the air entry value. Your pi b angle is the same as the initial internal friction angles. But air entry value, before air entry value, your soil still saturates. We don't consider this pi b angle because it is just internal friction angle. Beyond the air entry value, you can see a bit the gentle slope of your curve with respect to different metric suction. Then you will get pi b angle. Now it's 14. This 14 create additional shear strengths. Okay, we gone through theoretical approaches. What is the effective stress? What is the shear strength? And then for the laboratory test, we will get so water characteristic of permeability function, unsaturated permeability, and unsaturated shear strength. Let's take a look. Real application of such unsaturated soil mechanics. Okay, let's continue. This is the clear examples for the application of unsaturated soil mechanics. This is the capillary barrier systems to minimize rain infiltrations into the slopes. As you can see, we have a two-layered system, fine grain and coarse grain. Water, when it rains, water will flow along the first layer and then gradually infiltrate into fine grain. The fine material still have a lower permeability. It is a bit hard to infiltrate at the beginning. Keep rains, the rainwater penetrate into the fine grain. But you can see the infiltrated water flow through fine grain layer and goes to the drain. Cannot break through coarse grain layer. Why? Rainwater break through fine grain. This infiltrated rainwater cannot break through the coarse grain. Why? It is because distinctly different unsaturated hydraulic properties between fine and coarse. Okay, the blue is the fine grained soils. Red is a coarse grained soils. And then corresponded permeability function is something like that. At the beginning, coarse grains permeability much higher than blue, which is fine. And at a certain point of the matrix sections, the opposite is true. These coarse grain layers still unsaturated conditions. Under unsaturated condition, their permeability is lower than fine grain soils. See, for example, 50 kilopascal. The fine grain soils permeability is something like that, -5. But your coarse grain soils around -8. Water cannot go in. Based on soil water characteristic of and unsaturated permeability, which is the unsaturated soil mechanics, we fully utilize this mechanism to minimize water infiltration. I can say minimize rather than protect. Water can go in, but try to minimize. So we test it in the lab and then find out some the certain boundary conditions to implement to real project sites. So I did numerical simulations. First of all, I conducted CPG analysis and then conducted slope W and then sigma W. SIP W meaning water infiltration. Slope W is slope driving force and resisting force. And sigma W is the specific deformation of the slope. I just simply show you, I create original slope. This is simply draw and apply the rainfall. And this is the capillary barrier system, same as the previous one, and then put another layered system, capillary barrier, and then apply rainfall. This is the fine layer, coarse layer. And I tested index properties, soil classifications, specific gravity. You see 2.6 something, right? And porosity, and then unit weight. Yeah. And then water contents and optimum water contents. What is the optimum water content? We studied soil compaction, right? And then from the soil water characteristic tests, we obtain such soil water characteristic curve with respect to volumetric water contents versus matrix suctions. From this curve, I obtained unsaturated permeability with respect to matrix suction. We discussed previously, right? And then obtained saturated volumetric water content air entry value, just starting point, my air goes into the soils, and then residual things and fraudulent A and M parameters and saturated. And I conducted triaxial tests. We'll get Young's modulus, C prime, B prime, pi B angle. Okay, this is the hydraulic characteristics of our unsaturated soils. This is the mechanical properties of unsaturated soils. This is the port pressure distributions. This is slope, original slope. Plus 20 meaning 20 kilopascal. Zero, zero meaning water levels. And then 20 is the green, and then this is light greens. It means that whole entire slope is fully saturated. Only inside a bit, this area still unsaturated condition, very small. Slope failure occurred here. Only this line driving force rather than resistance force. That's why along this line, this slope fade. How about this entire area is remain unsaturated due to capillary barrier system. So this line will be failed, this driving force greater than resistance force. So let's take a look factor of safety. The original slope starts at 1.6 and decrease up to 1. Factor of safety 1 considered as slope failure because driving force exactly same as resistance force. But capillary barrier system starts at a little bit higher than original one, 1.6 something, and they keep down, still remain 1.45 something, right? To extent, when I worked in NTU, I also developed geo barrier systems, which is the same as the capillary barrier system, but I added up retaining wall mechanism. So fine grained soils dumped into the certain bag and then placed on here. And also put coarse grain. The green bag is the ASM, right? Allowed soils materials. Because this is a general configure the photos of the um, field tests. Because we apply plants in the bed. That's why we use the special soil materials for the plants. After this, here is the fine grain, here is the coarse grain to minimize water infiltration. The slope is up to 70 degree, quite steep. Real measurements. This is the real water record. But my port pressures remain negative. Good performance. And I've also conducted numerical simulation for the geo-barrier system. The green one is the original slope. When it rains, the factor of safety is the fluctuated. But slope 1, 2, 3, this is the slope 1, 2, 3. Remain constant in terms of factor of safety. This geo-barrier system can be applied to HDB projects, non-HDB projects, and then private, which is the slope failure areas. So we reinforced with geo-barrier system, and now it looks like something like that. Quite sustainable and then nature friendly. This is the HDB North Shore area. The slopes reinforced with geo-barrier system. Angmokyo area, we also applied second layer of geo-barrier system. This is the Frama slope near River Valley, near my place. This slope totally failed. So we apply geo-barrier system and capillary barrier system, hybrid. The total slope height is more than 20. The final construction and current status. Looks like greenery cover systems. The conclusion. The principles and the theory of unsaturated soil mechanics is required to describing the behavior of nature soils, which is commonly observed in the unsaturated soil conditions. And then some laboratory can be available for the practical applications. And then the unsaturated soil mechanics is still available in our real applications.